Hey everybody. Today we're getting into correlation. We're in a situation where we have paired data and the scatter plot for that data has a generally linear shape, like in this plot of iris measurements. So here I have 50 flowers and I've plotted the width of their sepals on the x-axis, the length of their sepals on the y-axis. You can see that as x gets bigger in this plot, y gets bigger generally at a constant rate. In a situation like this, we say the variables are correlated. We try to reserve the word correlation for variables that have a linear trend like the one I'm using here, although sometimes you will hear people use the word more loosely than that. We measure the strength and direction of a linear relationship on a scale from -1 to 1, and the number we choose is called the coefficient of correlation. It's denoted with the letter R. I'll show a formula for that in a little bit, but in general we're going to compute it with technology, so it's better just to talk about it a bit more abstractly and not referring directly to the formula. A positive coefficient of correlation indicates an upward trend, while a negative coefficient of correlation indicates a downward trend. Correlations can also be weak or strong. So here I'm showing 6 plots. The 3 on top have positive correlations, so generally upward trends, while the 3 on the bottom have negative correlations. And as you go from left to right, the correlation is getting weaker. The coefficient of correlation is getting closer to 0. So for instance, the 2 plots on the left have correlations of 0.9 and -0.9, respectively. There the values are pretty tightly packed along the line of best fit. In contrast, on the far right, the correlation values of 0.3 and -0.3, you've got a lot of spread around the line of best fit. You have to be really careful to remember that correlation is not measuring slope. Instead, it's a measure of spread. So in the plots on the last page, the top 3, the ones with the positive associations, the positive correlations, all have slope of 1/2, even though the correlations are very different. If you have a correlation of 1, that's indicating a positive relationship that is a perfect linear relationship. And if you have a correlation of -1, you have a perfect negative linear relationship. Notice again, we're not talking about slope here. We're just saying the points lie exactly on a line with positive or negative slope, respectively. Variables that have a linear relationship but 0 correlation look like random clouds, like this one. And in situations like that, we say the variables are uncorrelated. On the other hand, variables that do not have a linear relationship can have a coefficient of correlation equal to 0, even if they don't just look like random clouds. Here, for instance, if we were to compute that coefficient of correlation, we'd get a value very close to 0. But on the other hand, these variables are obviously associated with one another, in the sense that if you tell me the x value, I can make a pretty good guess about the y value. The formula for computing the coefficient of correlation is ugly. Here it is. In general, you should always compute this using technology, not doing it by hand. If you look at this formula a little more closely, you'll see that the denominator looks really similar to sample standard deviation for the x variable and for the y variable. In the numerator, we have sort of a hodgepodge of those. That ends up being relating to the covariance between those two variables, sort of how are x and y interacting. Let's close with a quick example. Here's a very simple data set. We have 5 observations of 2 variables, x and y. And we want to compute the correlation between them using technology. I use R, and in R, the command for correlation is cor, and then you just pass it the 2 variables that you have. Correlation is going to be the same regardless of what order I put these variables in, by the way. So what you're seeing here is me coding in the 2 variables x and y. Notice that I've kept the order exactly the same because I have paired data. The x's and the y's match up 1 to 1. Once I have x and y coded in, I do cor of x comma y, and in this case, I get a coefficient of correlation of about 0.787, representing a moderate to strong positive correlation.